of many, many questions I've received over the years about ground, and people are always asking, you know, what should I do? What's with these things that I'm driving into the ground? What's with these wires? Where do I connect them? All that stuff. And so I finally decided that I would put together a talk about this interesting subject, and maybe we can do a little myth busting along the way. So a lot of times I'm sure you've wondered what ground is, but I think a lot of us just accept it as a thing, you know, a thing that we can quantify or figure out exactly what it means. But I'm going to ask you to think, open your mind and ask yourself whether this really has meaning. You know, we see it all over the place. We see it on schematics, and we see it other places. All over the place, there's all those symbols. But what does it really mean? So you might say, well, it's kind of about this reference point. That we have this arbitrary zero reference in a circuit. It could be an energy state. It could be some common connection. You've heard all of those before, I think. And there's this, you know, because we're talking about ground, like the dirt beneath our feet, there's an implication of stability in that word. But, I don't know, it could be about the earth. It could be about physical objects in contact with the earth. It could be the Earth's charge state. It could be the distance to the center of the Earth, because that's the center sort of mass. It could be about even gravitational potential energy. And if you are familiar with gravitational potential energy, it's this very simple equation, mgh, mass times gravitational acceleration times the height. But what's the height? Is it the height from me standing on this podium to there? Is the height from me to some mountain somewhere? Or if I'm standing on a mountain, from that down to sea level? Is it to the center of mass of the Earth? Not clear. And if there's no Earth, then there's no kind of reference like that. We just have two masses. And we have Newton's law here, which is, of gravitation, which is pretty straightforward. And it just talks about the distance between these masses. And this is actually a lot like voltage. So voltage, if we look at it, is basically based on the electric potential. And we see here in a diagram that shows a charge and then another charge nearby. And the voltage kind of marks your relative positions within these fields. And so the charges may repel or they may attract. But what this is really saying is something about the amount of work you'd need to do to push them together or pull them apart. And that work translates to potential energy. So that's like giving you an idea of what you have to do to change the state here. And in this case, kind of like gravitation, it's a conservative field, which means that it's path independent. It doesn't matter which way you get there. You just get there, and it's that actual distance between them. But then, is there a ground for voltage? Well, not really. It's kind of this difference in this electric field. Where is zero? If I look from one charge, I get one aspect. I look from the other charge, I get a different aspect. And maybe there's something at the edge of the universe that I haven't encountered yet that is zero, but if you see that out there, please tell me, although you may not be able to communicate it back to me. That could be a problem. I may not know about it ever. So anyway, I don't see anything there. So what about current? So is there such thing as a ground state for current? Well, current is expressed as the time rate of change of charge. It factors in several of, well, at least two prominent equations in Maxwell's equations, and the charge continuity equation, which is also there too. But it's actually looking at the time rate of change of things. And so there's kind of no reference. It's like, how far did the charge move from time t0 to time t1? So I haven't found it there yet. Now what about circuits? We talk about circuits all the time. We have this common reference. You can see on this circuit diagram there's this ground symbol. And down in the bottom right-hand corner, you can see that there's, what, 5 different symbols for ground? Something like that. They're all apparently different in some way that I'm not entirely clear about, but they are different. And then we have this shield business around a pair of conductors. And where do you connect that? Is that the ground? Not really clear to me at all. And then we have digital and analog ground. So if you've ever done any mixed signal designs, you see that there is one ground where you hook all the digital circuits up and they have a lot of current, and so the ground is, in theory, bouncing around. I mean, there's a problem right there, right? The ground is bouncing around. And then there's the analog one, which is, in theory, not bouncing around so much. But what if those two grounds are not the same? In fact, often they are not. And that's why people want to separate those wires. They say that, well, one of them is going to move and the other one's not, and we don't want them near each other. And if we kind of connect them in a circle, we might get a ground loop, which means currents flowing around these different conductors. And you get these ground currents, which is almost an oxymoron, right? So here's a schematic representation of what ground kind of looks like. And we have a common return path for this example circuit here. So we have a voltage source and a resistor R1, and then we have another voltage source, and we have a couple of terminals we want to measure the voltage at. And then we have this circled in red node there. This is not node red, by the way. This node here with a resistor that's kind of a phantom resistor, and that would be the resistance of the ground system. So if that V1 is making some current flow in that resistor R1, then a little bit of voltage is going to develop on that phantom RG, right? And so you have to start asking hard questions like, what's the voltage where the V out terminals are? Well, it's a function of how much current is flowing through that V1, R1, and into the ground. And then it gets more complicated. So what's that voltage? Well, I'm not really sure, because I don't really know what RG is, and I don't know what that current is, maybe. So now I'm getting a little bit more confused. Now, AC circuits, things get a little more tricky. So we've got signals moving in time, and this is a representation of 3 phases. So there's got to be some zero reference, if you want to call that ground. But all of these 3 signals are moving all the time. And so where's the zero reference? Well, I mean, you could draw a line at the 0 point on that graph, but what happens, how do you get that 0? And while we're here, I'm going to take a minute and talk about phasors. Anybody played with phasors? If you took the extra test, I think you have to, right? So they're a convenient representation of the state of a circuit, an AC state. They give you kind of, you can play with currents and voltages and impedances and things like that. And as you see here, they can rotate with time. So that's rotating in the complex plane, and that's a projection in the real plane at the top there. But a lot of people over-apply these. It's only valid for a given frequency. I say monochromatic, and that's what I mean. It only works at one frequency, of course. But in our ham radio, we can kind of approximate that because we operate sort of at one frequency. We don't move it too much. So we can sort of pretend that it's at one frequency and get answers that are accurate enough. But we can really simplify things by using vector sums and things like that. Makes life a lot easier. And you can do it with multiple phases too. So if you have 3 phases, they rotate around like that. And you can do calculations with all the 3 different phases and figure out, what the voltage and the current and the impedances tend to look like. And we've done this on the exam, at least on the X-ray exam last time I looked. They give you little calculations you have to do for an RLC circuit and maybe just an LC circuit. And you have to figure out maybe what the impedance is or how much current is flowing and that kind of stuff. And you can do that really easily using phasors. And all you do is you just add the vectors or subtract the vectors. It's really easy. And that's a very standard process, very easy to do. So anyway, if you get a chance and you need to do a calculation like that, put the differential equations book in the drawer and use the phasors if that's appropriate. So back to our 3-phase idea. Now, some of you have maybe heard of delta configurations and Y configurations. So if we think about the Y configuration for a minute, we have these 3 phases, and then we have this neutral. And you could kind of call the neutral a reference of some kind, right? But there's a transformation that will take you from the Y configuration to the delta configuration. It's completely equivalent, completely algebraically equivalent. So you can just go crunch through this and you'll get the changes in voltage and current. And then when you get to delta, where's neutral? It's gone. So the neutral is kind of an overspecification of the situation. But now you don't have a reference anymore. And if we simplify this down a little bit more like what's in your house, we have neutrals and split phase. So if we have a split phase like that, you have something on your power pole, and it might be at a much higher voltage or it might be a similar voltage, and it goes into a transformer. And the transformer magnetically couples the energy from the light pole to your house. And if the transformer could stand off enough voltage, you could be 1,000,000 volts away and not be referenced at all to what's up at the power lines. And then you take this center tap on that transformer and you call that neutral. And you stick that maybe in a piece of metal in the ground or something like that, whatever the code cares about. And now you have something that you're calling ground, but it's not really referenced to anything in particular. With any transformer, you've dereferenced the voltages between what's on one side of the transformer and what's on the other, except for breakdown of insulation. And this is required by electrical code, but the thing to take note of is there's really not a zero reference. You just called it a zero reference. It's not really zero. Now, of course, as I mentioned, we have this conventions, the National Electrical Code, and I'm not here to talk negatively about any of that. But I do want to give you some stuff to think about around this. So we connect this to the earth, and I'm going to be more explicit about that now. And we have this big water pipe, for example, that's down in the dirt, and it connects to the dirt. And is dirt a really great conductor? Not really. It's a very unpredictable conductor. It depends on the type of soil and stuff. I have some graphs later you can look at, but it's generally a poor conductor unless you have some, ionic compound like salt in there and some water. And then it can get it to be more conductive. But can you still be hurt by a voltage differential between you standing a little bit away from the electrical box and touching the neutral? Sure. It's possible if there's enough of a gradient there. Now, you've all heard of ground fault interrupters. You may have one of these in your bathroom, right, or in the kitchen. And they're really cool devices, and they say ground right in it, so it must be referencing that ground, right? Well, not exactly. They're actually clever devices. So they have like a toroid, and they pass both conductors, the hot and the neutral, through the toroid. And if those currents are exactly balanced and matched, there won't be any net magnetic field there. And so they wrap another winding around that toroid to try and siphon off a little bit of whatever might be there. And if they see a voltage develop on that secondary winding, then they say, oh, something's wrong, and then it goes pop. And so what it's looking at is imbalance. So all it can say is, well, some of the current went somewhere else that wasn't in the middle of this toroid. And so I'm a little alarmed about that, and I'll pop the breaker. But is that really ground? Well, I don't know. If the current went somewhere, maybe not where you wanted, but I don't think we've found ground inside the ground fault interrupter. I mentioned ground conductivity earlier. Here's some charts about that. Even in the best of conditions, as it says there, it's hundreds of ohms. I mean, you can get it down by pouring a lot of salt water on things, but usually in things you found out in nature, it's like that. And then you can be several orders of magnitude, like 4 orders of magnitude different in other conditions. So this is like interesting information, but you have to be aware of it when you're setting up any kind of system. You know, if there happens to be current flowing in that particular direction, this might not be a safe situation because there will be a gradient across there. So just because we stick it in the earth doesn't mean it's a common conductor. And that's, it's useful, may or may not be safe. Now if we increase the frequency, we get other effects. So we have different kinds of soil, and they have these dielectric effects. And so they start acting more like a capacitor. So as we increase the frequency, you'll get more coupling perhaps. It depends. This might have interesting implications for your antenna system. So you might see the pattern shift around as you change frequencies based on the kind of dirt that's underneath your antenna, especially if you have a low horizontal. You'll see this because you get a lot of those kinds of fields. You get current mirroring, which tends to push the pattern around quite a bit more than the charge mirroring. Does this do anything for safety? Unclear. You know, if you're at a certain frequency at a certain distance with a certain soil conductivity, a certain dielectric constant, you might not see a gradient. Who knows? And if you bump the frequency up, you can see that there's a big difference for different frequencies when you're kind of in the low HF area, and then you get up towards VHF and it all starts to look the same as you get more and more of this dielectric effect in the soil. So, yeah, kind of interesting. It's a good thing to know about. I'm not sure that it references anything in particular that I could call ground yet, though. But of course, you've heard that antennas need grounds, right? We've all heard that at one point or another. But if you have a balanced antenna, like a dipole, there's nothing to, anything you do to it would unbalance it. So it has a nice symmetry about it. And if the currents are symmetric, there's no need for any other connection there as long as you can drive that adequately from some kind of generator, which we call transmitters. So it doesn't favor anything like that. And matches, even though they're kind of asymmetric, they don't really find any particular side of the antenna more interesting than others. So, you know, you've got this kind of gamma match, and you'll see that that helps you to match the impedance by moving you down the conductor a little bit where you feed it. And it happens to be on one side of the antenna, but it could easily be on the other side of the antenna. And it will affect the pattern just a little bit, depending upon its size relative to the driven element there. So that hasn't found anything super interesting. In fact, there's this thing called the delta match, which is perfectly symmetric and does a similar job. And so you can achieve symmetry if you really want it. There's these other things called ground planes. People have ground planes somewhere? Yeah, you may have one of those at your house or something. So ground planes have these things we call radials sticking out of them, and they sort of try to mimic the other half of the antenna. So you take half of the dipole away, and you make it kind of a phantom antenna. And so the signals sort of reflect, if you will, off those ground elements, and then it mimics the other half of the antenna. It changes the feed point impedance, but you can compensate for that. But the idea is that you can make the antenna smaller. Of course, you know, you're going to have a harder time driving it. The radiation resistance is a lot lower, so you're going to have to worry about effects of losses around those radials. And if you put them on the dirt, you will find that you get more loss from them. And that's why you generally want more than the radials they give you. Most of these antennas, they give you like 4, 3 radials. That's generally not enough to suck all that energy out of the dirt. So you want more if you can do it. And they don't actually have to be on the ground, right? They can be up in the air. And if they're up in the air, you can tune them to the frequency of interest, and then you can get away with as few as 2. That's what the Motorola guys found out. So you don't need that many. So they're not really connected to the Earth. They just are there as a part of that antenna structure, making it work a little differently. Now, balun, right? The whole idea with a balun is it connects to ground, right? Or let's just say the chassis of your radio. But baluns aren't really mystical devices. They're transformers. And like I mentioned earlier about the split phase in your home, they decouple the voltage references, and you can recouple them in a way that you want. So if you have a voltage coming out of your transmitter in your radio, and then the chassis is one side of that, and there's current flowing out and going back through the chassis connection, which is often the coax shield, you can put that in the primary of a transformer, and then you can decouple it voltage-wise from the transmitter, and then have, say, some ladder line that will be fed symmetrically without being referenced to the voltage in the transmitter. So that's the idea there. There's no real earth ground necessary. It's just a transformer used to change voltage references around and isolate things from one another. We often hear, don't use the neutral or the safety as ground. And a lot of times you see publications that say, put a ground rod in. So you go out and you rent some equipment, or you get your shovel out, or you get a big water hose and you kind of open up this big hole and you shove this thing 6 feet into the dirt. What are you doing? Why are you doing that? You have to ask. What's the purpose? So it's a big undertaking. And there is a reason I'll talk about later why you may want to do that, but it's certainly not for RF. When you couple RF to that, it may work better, it may work worse. You might get more noise, you might get less. Hard to say. But it's not an essential thing that is needed for RF. Power supplies really confuse me. So I have this power supply. This is a Linko power supply, and it's got this screw on the back, right? And the screw seems to go right into the aluminum chassis of this thing. And there's also these terminals. I got plus 12, and I got ground, or minus side of that plus 12. And then I have this cord with a safety ground that plugs into the 3-prong outlet. And I don't know quite what to do with this thing. Where do I connect that? And I'm just confused. Is your head spinning? Because mine is. You're in this field that's changing with time, changing with position. Where is 0 volts? I'm not really sure where that is. It's spatially dependent. I can move over here and it's all different. Even in the whatever fields are coming from the radio is in my MacBook here. I don't know where I am. I can induce, currents can be induced places, and I'm not sure where they're gonna land or how big they're gonna be. And so I'm just really confused. So what I realized is, this is an impossible thing. There is no ground. It's all relative. Everything is in motion all the time, we know that. But it's also in motion with respect to time. And the best that we can do, in my opinion, is to sort of differentially stabilize everything as best we can so that we're not going to get hurt and we're not going to get signals in places we don't want them. So what do? I have 3 categories of recommendations: shield, isolate, and stabilize. And I think if you follow this principle, and I operated for years on a 2nd floor apartment this way, if you follow these 3, I think you can operate your station in a safe and non-interfering manner. So let's talk about shielding. Shielding is, we sometimes call this Faraday shielding. It's because of Faraday's law and how it basically, when you have something encapsulated in metal, it eclipses the time-varying electric fields, which eclipses the time-varying magnetic fields that accompany that based on our understanding of Maxwell's equations. And so this keeps these changing fields from inducing voltages and currents in places we don't want them. So we can do it in both directions. We can keep bad things from coming in or keep bad things from going out. It works in both cases. So it avoids, inducing currents in your house wiring and other things like that. And you can see this in amplifiers. This is an SB200 that I happen to have. And you can see that they have these metal plates, these aluminum plates, because aluminum is a pretty good conductor. And you have the RF deck in one, the power tubes in the other quadrant, or third-ish. And then you have the DC power supply in another part. And this keeps them all relatively separate. And you just drive that E field to 0, the time-varying E field to 0. And that keeps the time-varying magnetic field at 0 as well. So that won't induce things. And you can still pass a static magnetic field through there, just not a time-varying one. The next principle is isolation. So we try to avoid common mode currents, mostly, and reduce those leakage fields. So we we want to make sure that the things that are functional elements in our stations stay doing the functions that we designed them to do. And so we put these ferrites on, and the ferrites make the wires sort of into much better inductors than they are on their own. And that's like putting an inductor in, and keeps the currents from happening in places you don't want them to be. And you can see that the person who drew this diagram that I kind of stole actually fell for the ground thing, because you can see all these ground connections here that are not necessarily doing what you want, because that may allow some communications between the systems that you don't want to have happen. But it's basically a low-pass filter, an LR filter, that will, you know, the inductors, I always think of them as wires at DC, because they're just a ball of wire. But then as the frequency increases, they look more and more like open circuits. And so you can see that the low frequencies will get through, but the higher frequencies not so much. And you know, you can see this is a single pole roll-off over here, 3 dB per octave kind of deal. So if you wrap more turns around the ferrite, you get more inductance. If you put a couple in series, you can get another pole in there and get it to fall off a little faster. And I am a big fan of clamp-on ferrites. So I take these things and I sprinkle them everywhere. I was recently having a problem with when I swung my hex beam over towards the stove would kind of go nuts and crash. And so I just got a bunch of these clip-on ferrites, and I got behind there and I wrap, and then turn up the transmitter and everything's good to go. But you do have to be careful about the ferrite mix, because they're not all the same. You want ones that are going to give you a reasonable, because they're not completely linear devices. So you want to make sure that they're giving you enough inductance at the frequency of interest, because some of these ferrites don't have the same mu, which is how we measure this, at different frequencies. So you got to watch out for that. And lastly, and this is a kind of a cheap trick, but it works really well, is stabilization. So we want to try and put a low impedance, sort of like put ourselves connected to some low impedance sort of thing within all of these time varying and position varying fields, and reduce the gradients to the point where we're not going to get injured, which can happen. Anybody ever had an RF burn? Yeah, that's not fun, is it? So you want to try and get rid of that. And sometimes these things can be enhancements to your antenna. And what we do is, well, and you can see in this little diagram here, we also have this earth connection, but I'm going to ignore that, is use counterpoises, quarter wave lengths of wire, roughly on the bands of interest. And they don't have to be super tightly tuned. You can just take them all and have one wire per band, and then bundle them together with a tie wrap or something like that. And then kind of run them around the baseboards or run them outside or something like that. And they will become part of your antenna system. But if there's any extra, voltage moving around, say on the chassis of your amplifier or something like that, this will stabilize them quite a bit within that field. But you have to be very careful about the ends. If you've ever had the end of an antenna near something, it can arc over. There's very high voltage on that end. So we have high current in the middle and higher voltage at the end. So with all of this, what happened to ground rods? Well, my opinion is, if you're not worried about lightning, you're mostly wasting your time with them. They are really there for lightning. They can, like I said earlier, they can make things worse. They can give you more noise. They can give you less noise. They can give you intermittent noise, all kinds of things like that. And on a portable antenna, I just take them off. So I had this antenna called a PAC-12. I don't know if it's still made by Pacific Antennas. And it's my go-to antenna to take out in the field. And it has, its base basically had a wing nut to connect a bunch of radials. And then it connected the shield of the coax to the spike that goes in the dirt. Well, you know what I did? I took that off first thing and added more radials and also made the coil go up higher. That's another separate talk. But that antenna performs like gangbusters. It's great. So when I was still living in an apartment, I had 800 watts, 7600, and a couple of different tuners, and no grounds anywhere to be seen. And so I used those three principles. So I shielded things as much as possible, and the amplifiers were all shielded, and I made sure that that shielding was tight. And then I put ferrites everywhere. I sprinkle them on every wire that goes everywhere, especially with the ones that go into the house wiring. And then I had counterpoises for all bands, and I put them around the baseboards. And it worked great. And you know, it's kind of unbeatable. And I wanted to give you one more word about counterpoises, just so you understand. They're kind of like a quarter wave monopole. And if you have looked at, say, impedance variations in a transmission line, you can see that you get a flip in the impedance every quarter wavelength. So what looks like, you know, and that's true at any point on there. So if it looks kind of inductive in a quarter wavelength, it'll look capacitive or something like that. So what you're doing is you're taking like a high current point. You pump a lot of current into one side of that. The other side, the voltage flaps around because there's no boundary condition out there. And it will kind of radiate like a part of your antenna system, but it will kind of try to stabilize that voltage near where you are. And this really does prevent RF burns. I've had the experience personally. So, but again, they have to be matching that frequency. But watch out for that high voltage. Be sure you fold them over and tape them on the end. And radials on the ground, like I mentioned earlier, are kind of like a detuned counterpoise on the dirt. And they provide that mirror, and this works very well with lots of radials. I find somewhere between 64 is way too much. But I have used 39 radials when I have the time and the energy to put them all out. And the antenna really works well. You know, of course, everything anecdotal is a bit suspect, but I worked Antarctica 10 watts from Stanford. It worked with this little antenna. So that's not definitive, but it does show that it at least works. Now, what do you do with all those ground lugs on the back of things? My recommendation is you kind of tie them all together, maybe use some low inductive braid, something like that, and put them all in the same voltage spot, roughly, and hook your counterpoises to that. And that will keep the whole shack, all the equipment, sort of at the same potential, minimize the probability of getting any RF burns, keeps that gradient to a minimum. And it's probably not a good idea to connect this to the ground rod, because I've seen people do this. So we'll talk about lightning in a minute, but it's probably not what you want to do for that particular reason. And then about those ground lugs, you know, I took this radio out, and I think I brought it to field day or something, and I put it back after field day and stuck it back in the shack. And I didn't realize I'd forgotten to connect that ground thing for months. And then when I went to put this talk together, I went to take a picture of it, and oh, it wasn't connected. And so it didn't really make any difference. You know, this is just insurance to try and keep like the outer shield of the coax kept things at roughly the same potential, but this is kind of insurance for that. And all this stuff also applies to your HT. If you have an HT, there's no ground except for you. You're the salty water bag, and you're providing actually the other half of the antenna, and not a very good one at that. And so you want to make it more efficient, that is, add a real counterpoise at a quarter wave length. And it's 19¼ inches for 2 meters, and it's a third of that for 70 centimeters. And a 1/4 inch ring lug fits very nicely over an SMA connector, if you've ever looked. And so you can make one of these things, and I've actually seen several S-unit improvement on repeaters that have S-meters. It really makes a difference. But again, if you touch the end of that thing, you will get a little bit of a shock, even at 5 watts. So watch out for that. So I want to shift gears now and talk about lightning, which I've alluded to but haven't talked about yet. So we're going to go back and talk a little bit about DC and clouds. And you can see some clouds here, and they build up charge because of friction with the air molecules and other effects inside the clouds. And generally, but not always, they're negative on the bottom and positive on the top. And the corresponding dirt on the other side gets the reverse charge because of the electric field pulling things in one direction or the other. And these things can cover big chunks of the Earth's surface as they do their thing. As I was coming here, I flew past a 80-mile diameter thunderstorm, and it was doing a very good job of covering the Earth's surface with a lot of charge. So they can be really big. But what we want out of this as hams and as homeowners is a safe discharge, or some way of safely equalizing those potentials. Now, here's a very simplified model of a lightning strike. Something like this. We have this intense electric field, and it kind of rips the electrons away from the atoms, and the nuclei are kind of being pulled apart by this field, and then suddenly it starts conducting, and as it conducts, it gets hotter and hotter, and that heat causes more and more ripping away of things, and these ions, which are the free charge carriers, become conductors. And then at some point, this charge equalizes. You flow the current down there, and the states get closer to the point where the thing dies out. And we really don't want this in your shack. This is bad news, right? Definitely don't do it. Now, there's lightning rods, and lightning rods have this sharp tip, which you probably noticed. And that's because this high curvature of the tip of the lightning rod causes the charges to not repel each other as much, and so you get this charge concentration at that tip. And wherever you have more charge, that means you have more intense electric fields. So the idea with the lightning rod is that you electrically lift the surface of the Earth up high somewhere, closer to the clouds, and then you have this tip which has a large concentration of charges, and then you try to get the discharge to happen there. It doesn't always work, but most of the time it works. And you get that discharge, it's a huge amount of current, it goes flowing down that large conductor and equalizes in a way that's not in your home. It's maybe above your home, but it's not in. So that's what you want. Now you may have noticed that antennas look a lot like lightning rods, right? They have a high rate of curvature, and they tend to so-called attract the lightning because they lift the charged state up off the dirt into the sky, and they have this curvature and sharp edges and stuff like that, and bam, and they're really efficient conductors. And if they go through the coax, that's not good. So you may want to take care of that in a way that doesn't make that current flow down your coax with a nice big chunky piece of wire, and that will get it down there reasonably well without interfering with the RF state too much. Now, this is where we get back to the coax and the station ground. Because what I've seen is that some people will have the coax from their antenna come into the shack and get screwed into the back of the radio, and then that little ground wing nut on the back of the radio gets connected to the ground rod. Anybody know why that's a bad idea? You're inviting the lightning into your home. Not good. It's not a friendly neighbor. So you really don't want to do that. You want to have something outside that is something like one of these polyphasor devices or something like that that can become a conductor when needed and safely get that charge state equalized outside the house, outside the shack. Otherwise, you are not going to be a happy camper. I guarantee it. So get that stuff out. And when you do, if you're in an area that has a lot of lighting, I'm not. I'm blessed that way, I guess. But consult with somebody who's very experienced at this and get it done right. So after all of this, what happened to ground? Kind of went poof, right? Except for lightning, I couldn't really find anything in here that showed me where there was some reference. And we learned that everything is all relative. There's no distinct reference anywhere except for one that you say is a reference. And that's up to you. I mean, the electrons don't care. And we also learned that the Earth is not a reliable conductor. It's a lousy conductor, as a matter of fact. And it's also a lousy dielectric. So it sort of looks like a capacitor, sort of looks like a resistor. It changes when it rains, and it changes with the humidity, and it changes with where you live. So with that, what can we do as hams? Well, shield our equipment, as I mentioned. Isolate the things, sprinkle those ferrites everywhere, stabilize things within that RF field, and except for lightning, you can ditch the ground rods because they're a pain to deal with anyway. And then have fun on the radio because that's the most important part. And what you're seeing there is a picture of our California QSO party set up, 1,500 watts at a rented cabin. We had a hex beam in that case and a few other antennas scattered about. Not a ground to be seen. Worked great. We actually set some records. So, I'll take questions. Yeah? Yeah, static discharge is a lot like lightning. So it's a similar case. You can put like a gap, and then it'll arc across the gap and equalize the charge again. But it's essentially the sort of degenerate version of the lightning case. Yeah. About the counterpoises? I think you might find some of that in the amateur radio handbook. Those kind of places, they're very simple, you know, just quarter wave. Not much to it. Yes, over here.
So, if I use one-to-one balance, is that going to be my equalization?
So,
If I come on, I basically I'm going to reductively couple my coax to my antenna.
so you're going to use like a one-to-one transformer?
Right, one-to-one transfer.
Yeah, so you're decoupling the voltage. Okay, so the current, well, the power will stay roughly the same. Of course, there's losses in the ferrites and the wires and such, but you're just decoupling the voltage reference.
So, that's it.
I mean, if you want to feed like a dipole, and the dipole has balanced line coming down, then a one-to-one balun will decouple the voltages so that you don't have this imbalance where, you know, the chassis of the radio is connected to part of the antenna system, which may not be what you want. Back there.
With the fire department, when we're transferring flammable liquids from one container to another, to prevent static charge, we would typically count as ground rounds. Another technique that we've been using is to take aluminum foil, throw that on the ground, and connect with that. And that work for your grounding.
Yeah, well, that's another case of stabilizing, of safe discharges and equalizing charge states. You know, same thing for airplanes, you know, you connect that wire and you're just trying to get the airplane to be at the same potential as that patch of dirt. And it's really just a patch of dirt you're talking about because you move 10 feet and it's different. Yes, over here.
How do I convince a building inspector when he's looking at my antenna that this is for lightning protection only and not part of the electrical system?
Good luck.
I'm serious, because when I went to get my building permit, they said, you got any electricity going through here? No.
So the only recommendation I would say is get a professional engineer because they have the necessary credentials. Not that that makes them smarter or anything, but they might believe somebody with a PE certification. I don't know. Yeah.
For the inspection and then.
Yeah, there you go.
Well, I'll tell you.
Yes, over here.
I do have Ward Silver's book. I can just, hey, look here.
With respect to lightning protection, is there anything Ward Silver says that you disagree with?
No, I think he's pretty much on message. Yeah. Yeah, that's a good book for that. Over here, in the back. Talk loud. Well, sort of. I mean, you'd like them kind of straight as much as you can make them. And if they're off the ground, that's even better because they won't get detuned as much. But they're kind of okay anywhere. In my experience, it doesn't matter that much. Yeah.
Do ferrites erode, decay, or do you have to replace them?
Generally not, unless you make them very hot, which can happen if you get a lot of heating from being way up on the hysteresis curve. And so they can get hot and degrade that way. It's a ceramic with a high mu material in the middle of it. So the ceramic keeps it pretty good against weather, if that's what you're asking. Yeah.
Go back maybe 100 years, we see with the crystal, this reference, you've got to have that ground water pipe. You know what the origin?
Yeah, that's the other half of the antenna. You know, an antenna cannot be a single radiator. There's always another half. Yeah, you know, a water pipe is a reasonable other half of the antenna if you don't care about the feed point impedance or the pattern. So it's something. But yeah, right, you know, like that's the HT case as well. You know, you have this HT, and if it's just sitting on a table that's not conducting or anything like that, and you key it up, it's not going to work nearly as efficiently as if you put your hand on it. But if you have that other actual metal half of the antenna, it's going to work even better. Okay, one more, and then I think we're done. Yeah, in the back. Talk loud.
Shielding I got, and ferrite was around power where you lost me with count.
So generally, my way of knowing that I need one is I've got RF in the shack. So I've got, I'm touching things and I'm feeling the burning sensation. That's a surefire reason to consider this. Other things where, you know, the lights are lighting up and the alarm system's going off, generally, you know, that also indicates you have large field gradients nearby. Yeah, in that case, you want those counterpoises outside the house if you can possibly do it. All right, I'll do one more. Go ahead, in the back. I have done that. It's not as good, right? And I've run it around the baseboards. It does do better than nothing. If you can get them outside, that's all the better. All right, I think we're out of time, but I appreciate all of your questions and